Yep. Thanks everyone. So I'll be talking about some work we've been doing on optimizing OFDMA systems, and this is joint work with Alexander Stolyar, who's actually also here. He made it to this presentation to help me out. Okay. So what I'm going to be talking about is start with giving an introduction, just to set the problem and describe some of the models I'm considering, and then I'll jump directly into the algorithm for the constant bitrate flows. After that, we'll talk about the algorithm for the best effort traffic. They're related but not identical. So, okay. So why are we studying this? I guess cellular systems have come a long way since inception back 30 years ago. Almost 1/3 of the world's population now uses cellular phones, and the amazing thing is the amount of technology development that's happened around this concept. So we started out with TDMA and then evolved to code division multiple access, and now finally orthogonal frequency division multiple access systems are being standardized, and in some cases even deployed in the case of WiMAX. But all of the different forums and systems are evolving towards that, primarily driven by the wider bandwidths that are required to serve the provide the higher data rates that is expected or being demanded by various consumers. And similarly, in the wireless LAN framework, it started out with 802.11b, which was sort of a CDMA based system, and quickly migrated to OFDMA, which is also in a sense has some of the features that are tied to generic OFDMA systems. So the goal is in general to study how OFDM systems can be optimized. I think there's a lot of research going on around that topic, and our work fits right into that context. Okay, so why is OFDM different, or in what way is it different that we can exploit to optimize systems? So the time scheduling aspect of it is something that's common across that and the previous systems like EVDO or UMTS, HSTPA, etc. But what's different is with respect to the frequency domain scheduling. So multiple users can be assigned on a single time slot, and the unit of resource allocation is highly granular. A small number of subcarriers can be assigned to the users, right? And this gives us a big leverage in terms of how we can do resource allocation and optimize the system. Another important aspect that's unique to these systems is the dynamic power allocation, which is basically being able to allocate different levels of power on different subcarriers. So essentially, you're able to shape the frequency domain spectrum, which wasn't possible, for example, in code division multiple access systems. Okay, so the other important aspect is the ability to do interference averaging. So initially, the systems were based on frequency reuse because you had to do out of cell interference mitigation in some way. But with OFDM and frequency hopping, you're still able to do universal reuse, like the code division multiple access systems. And that's because of being able to do interference averaging. So a user in a given sector sees the average interference from the neighboring sectors, even though you're doing a power allocation differently, perhaps, on different subcarriers. And in combination with interference averaging is the fact that you can control the amount of averaging that goes on, which is very important for our work. The idea here is that you can divide the whole set of subcarriers into sub-bands and then restrict the frequency hopping within sub-bands, right? So by doing that, you're only achieving interference averaging within a sub-band, okay? So this is an important idea that I'll probably repeat one more time, and you can see how it applies to what we're going to talk about. So the bottom line is the OFDMA systems are highly flexible and provide a lot of hooks that we can exploit to do better resource allocation, resource management, etc. And in general, I think the scalability aspect of OFDM systems and the fact that the uplink is orthogonal with time synchronization are the basic drivers for system switching to OFDM. Okay, so when we talk about out of cell interference mitigation through resource allocation, one can consider a variety of ways to do that. The traditional approach would be sort of static, say frequency reuse schemes. So in the beginning, when we were doing IS-136 TDMA systems, typically the reuse was as bad as maybe 1/7 with omnidirectional cells. But of course, GSM systems now are much more advanced, and they do frequency reuse of 1/3 or 3/9, etc. But it's still a static frequency reuse. You do frequency planning, and then you deploy the system with that particular frequency reuse. And it's typically designed for the worst case, the user at the cell edge, right? But you can do a little better than that even in the static case by doing something called reuse partitioning, which is to allow sort of fractional reuse within the sector. We'll talk more about that. That gives you some improvement in some cases. But the main point is it doesn't adapt to any kind of traffic dynamics at all. On the other hand is the dynamic approach to out-of-cell interference mitigation, and that can further be classified into either centralized or distributed. The centralized approach is, an example of that is joint scheduling across or joint resource allocation across multiple base stations. And this is of course complex. You're collecting information from multiple sectors, base stations, and then making a decision for all the sectors put together. So you can imagine how complex that scheme would be, and at the same time it can use significant backhaul bandwidth depending on how much information has to be collected before a decision can be made. So although it's optimal, it may not be a feasible or some preferred approach to doing this. So what we are going to focus on is the distributed approach to interference mitigation, where base stations assign resources to users independently of other base stations, but in a way that can still provide some level of interference mitigation. So by defining rules with which each of the base stations does resource allocation, we can create some interference mitigation to happen. Okay. I would say that if you're exchanging some information between base stations, it could still be called distributed, but in our approach we are not considering any information exchange at all between base stations. Okay, so why are we so interested in interference mitigation, especially out of cell interference mitigation? The obvious reason is of course the macrocellular systems, where the cell edge user performance is limited primarily because of out of cell interference, because as the cells are shrinking, the SNR from a single sector is pretty high. That's not the limiting factor, but more the fact that they experience significant interference from the surrounding cells or sectors. So clearly any scheme that works to mitigate that would be beneficial, not just for the cell edge users, but through them for the whole sector itself. Another application is to femtocells. For those of you who are not familiar with the concept of femtocells, it's basically the idea of deploying small, low-power cellular base stations within buildings or homes to provide local coverage. Okay. Now, when you do this, there is an issue with how the femtocell that uses essentially the same spectrum interacts with the macro cell. You would think that you could reuse the same frequency both inside the cell, inside the femtocell and outside, but there are various issues associated with that. For example, one is to do with having to restrict users from using the femtocell when they're just outside the house, for example, right? So they should, when a user is just outside the house and he's talking to the macro cell, he's transmitting high power, which can affect the femtocell performance. Ideally, you would have liked to hand off that user to the femtocell, but for reasons such as privacy or not allowing anybody to access your broadband backhaul, you do not want a user that's close to the femtocell to be using the femtocell. So this causes a lot of interference if it's on the same spectrum, right? So there's a lot of issues around doing that. The other issue has to do with reduced capacity of the macro cell because of femto transmissions, etc. Right? But the bottom line is the industry is moving, at least in the beginning, to use different sets of frequencies for inside the femto cell and outside. And with schemes like the ones that I'm going to talk about, we improve the efficiency by aggressively allowing for intelligent frequency reuse. And the third broad application area could be dynamic spectrum access, which is becoming increasingly popular, and it's related to some of the cognitive radio work that's probably going on here. The goal here is to harvest a spectrum that's unused, right? And clearly, as this concept takes off, you need better and better algorithms to decide which chunk of spectrum you want to use in what band and etc. So there's some element of cognition in some sense, although here it's driven by the network rather than the handset. Okay, so that's as far as the applications. So now I'm just going to give you a brief introduction of what the fractional frequency reuse concept is, and then jump to the algorithm. So the basic idea of fractional frequency reuse is starting off from regular frequency reuse, but making it much more granular in terms of dividing users in a sector into finer sets or classes, and then assigning different frequencies for usage for those classes of users, right? So in this example, which is actually not optimal, I'm showing that users that are close to the base station all can use the same frequency in all of the sectors, but users that are near the edges, they use some sort of reuse pattern, right? And we call something like that a fractional frequency reuse scheme. As I mentioned before, OFDM allows us to do this not just in terms of frequencies, but also through power, right? So you could think of soft reuse schemes where one band has, as a whole, one subband has less transmit power than another subband, which is not a hard reuse like not using the subband, but it still creates less interference to neighboring sectors on those subbands where you're transmitting less power, right? So we want to exploit that aspect, and we call that also fractional frequency reuse. So even though a sector may use all of the frequencies, if it's transmitting less power on one of the subbands, it's like having a fractional frequency reuse pattern. And the whole game here is to be adaptive to the locations of the cells, the kind of user distributions, and the traffic patterns, etc. Yeah.
So here, the algorithms you tell us do have coordination between the base stations, right?
No, there's no coordination between base stations.
Then how would you do this selective power?
Right. So we'll talk about it when I describe the scheme. You'll find out. By the way, if you have any questions at any time, please stop. Okay. So why are we interested in doing such fractional frequency reuse schemes? The reason is because, of course, we want to improve or do interference avoidance and improve throughput. But the point I'm making here is that you could pitch this as something that's really useful for improving the cell edge throughput, but it's more than that. You can actually improve the overall sector throughput while keeping the fairness the same. So if you decide to maintain a certain ratio of rates between the center users and edge users, or require a certain minimum rate throughout the sector, you can maintain a fairness criterion like that and show that you can do overall have a sector throughput improvement. Okay.
Do you have in mind downlink versus uplink?
Right. So what I'm going to talk about mostly is for the downlink. That's what we're focused on, but we have some thoughts on the uplink as well. And things are slightly different on the uplink for some reasons. Maybe I'll mention that when I go through this. The main reason is the amount of information that's available is not the same, because here we're using mobile feedback to make these resource allocation to work, whereas on the uplink, what you measure is different, right? You're not able to measure what the interference that the mobile causes to a neighboring cell easily. as easily as in the downlink. Yeah, so what I'm going to focus on today is mostly downlink.
So the resource allocation problem here is only power allocation because the frequency is fixed.
Yes, I'm going to describe the model right now, I think. Okay, just give me a minute. The next slide is the model. But here I just want to make the point that I sort of already made. So here is one example of a simple resource allocation strategy that leads to fractional frequency reuse. So here I'm showing two sectors, A and B, right? And let's say there are four slots in a frame. Having a simple rule like saying that in slot 1, both sectors will transmit to good geometry users or users with high C2I, right? Remember that mobiles are feeding back the average C2I for suddenly. Let's say they're just feeding back the average C2I for the whole band. Even then you can do something, is what this is showing, which is based on rules or priorities that you do assign to usage of subcarriers and to users. So here I would have a rule for sector A such as saying that these subcarriers starting from the lower end have higher priority. Or you can put more power on these subcarriers starting from here while that one starts from the top, right? And in terms of slots, you give high priority to users that are mostly in good C2I conditions, and slot 4 or going in this direction to slot 4, you give priority to users that are in poorer conditions or closer to the edge, right? You can see how this can create patterns. Of course, this is not an optimal strategy, but through such priority schemes, I'm just showing you that you can create a pattern independently. So it sort of gives you a rough answer to the question. Without having to coordinate between base stations, we can force some sort of frequency reuse pattern. Okay.
I'm sorry, I'm just losing it. What is 1, 2, 3, 4?
These are time slots. So let's say you're making a scheduling decision for each of these slots, right? And these are subcarriers. So yeah, basically what we're saying is in slot 1, you assign all the good geometry users, for example, right? And then you start giving priorities actually to users that are further and further away from the base station. And you do this similar thing in both the sectors, right? You get naturally some separation in the frequency.
Surely this is not fair.
Sorry?
Fairness is not taken care of.
No, yeah. Here I'm just illustrating it, right? You can throw in fairness along with priorities. This is how our old scheme used to be, and now we refined it with some new algorithms. But this gives you a good idea of how things happen. Okay. Yes.
What's the difference between bar 4 here and bar 4 on the other side? I'm not getting the...
Right. So the bar 4 here shows how much. The color here shows how much power is being transmitted. So when you're scheduling users near the edge of the sector, you're concentrating the power onto fewer subcarriers because they have very low C2I. You cannot spread your power. I mean, there's no reason to spread your power, right? So by concentrating the power on a smaller number of subcarriers, you can schedule somebody else with a small, provide 85% of the power on these subcarriers and 15% of the power there, for example. And you do the same thing on another sector, but on a different set of subcarriers. So if you think about it, the high power one and the high power one here don't interfere with each other. This is the overall idea, but this is not the actual algorithm. Okay. All right. So to just be more specific about the model, so what we are going to assume is all of our subcarriers are partitioned into subbands. Okay, so we'll have a fixed number of subbands, and the subbands can be thought of as logical subbands, whose physical subcarriers are either contiguous or distributed across the whole band. I mean, you may do one or depending on whether you want to do diversity scheduling or whether you want to do channel aware scheduling, things like that. And as I mentioned before, we assume that we have frequency hopping within each subband. And the reason for this is to achieve interference averaging. But the point here is the hopping is restricted to within the subband, so that you average out the interference from a neighboring sector only within that subband. So if the interfering base station is transmitting on transmitting different power levels on different subbands, you don't necessarily average out all of that, right? So you only see the average of the interference in a given subband. Right, and in terms of scheduling rules, the base station can schedule multiple users in each subband in each slot, and we assume persistent scheduling for CBR traffic, which basically means that if you assign a certain slot in a certain hybrid ARQ interlace, then that resource is retained until the activity dies. So I'm thinking about something like voice over IP traffic, where whenever you're active, you get a packet every 20 milliseconds. So there's no reason to change the schedule. So we call that persistent schedule. Now, the other crucial aspect of this is the channel quality information reporting that's used by the algorithm. What we are assuming here is that you have subband specific SINR information fed back by the mobile. So there's two components to the SINR. One is the signal strength of the SNR, and then the amount of interference you really see. Now, the interference is sort of the average from all of the sectors in that subband, right? What we need is only the average interference. So we're not trying to schedule around the fast fading of the interference, but more to adapt to the average interference levels. So although your SNR based CQI might have to be very frequent for doing channel aware scheduling, the interference reports can be relatively infrequent. Okay, so that's the point I'm trying to make here. But the bottom line is the base station can put together the two components and then have an SINR for each of the subbands. Okay, and the EVDO, RevC, or the ultra mobile broadband specifications conform to these requirements. Okay, so now I'm going to jump to the description of the actual algorithm. Okay, so as I said, this algorithm is for constant bitrate traffic, and by that you should just imagine voice over IP. So it's basically we have users going active or inactive, depending on whether they're talking or not. And during the active time, a constant size packet is received every 20 milliseconds or periodically, right? And yes, you need to transmit these packets as soon as they arrive, but there is some level of delay tolerance because it's voice over IP. That's the difference between pure circuit and voice over IP. So you can the delay can be a few, another 20 milliseconds, for example. Okay. So what are we trying to achieve in this context? So if you had a system all with just CBR flows, then and all of them are at the same rate, right? Then your real goal is to just maximize the number of users that can be accommodated in the system, right? Because they're all identical traffic flows. Okay, so and of course you want to maximize the number of flows for a given amount of bandwidth and power, right? And what is the algorithm going to be doing? Each sector is going to allocate resources to users in a selfish way without any coordination. We mentioned that, and as a result of this selfish behavior, each sector is actually optimizing its own objective, but the objectives are set up so that you can actually achieve the desired interference avoidance and the fractional frequency reuse patterns without any coordination. Okay, so that's why we call this self-organizing, and no explicit frequency planning is required ahead of time.
When you are allocating channels, it's like discrete set, or you can take continuous set and you can also assign some fractional subcarriers.
No, we do assign discrete sets.
So it's an integer kind of constraint.
In the actual allocation, but you will see that in the algorithm it doesn't have to treat it that. I mean, it doesn't treat it as discrete sets. So let me explain the algorithm. But the answer to your question is the real allocations are discrete. Okay, but the way we arrive at the allocation decision treats it as a continuous set. Yeah.
Do you have specific, basically, motivation to prevent the inter-cell coordination, since you have the infrastructure anyways, right?
Oh, for bases to talk to each other?
Yeah.
Well, as I said, it's more complex. I mean, when you say we have the infrastructure right now, the way it's set up is base stations talk to what's called a radio network controller, right? And it's the radio network controller can forward information back to other base stations. It's possible, but there is delay incurred because of that, and also it's a question of how much information you want to send. Yes, maybe to a limited extent it's possible to do that, but to make instantaneous scheduling decisions based on aggregate information from all the base stations is impractical, right? I mean, right now the schedulers are sitting in the base stations. So if you have to convey all of the information back to all of the bases, and they still have to make a distributed decision, I think it's just too complex. But I agree. I mean, maybe you could exchange information to a limited extent, and we are looking into that as well in terms of current work, but it's not captured here. Okay. All right. Yeah, but I think in either case, the bottom line is that this doesn't require any planning ahead of time, which is very important, because when you're deploying base stations, you don't want to be trying to do frequency planning.
What is it for?
The fractional frequency reuse that I was explaining. Okay, so how does this algorithm work? I mean, as I said, it relies on feedback from the mobiles, right? So here is a simple illustration. Let's say this base station is transmitting on 2 subbands, and it's transmitting more power on this pink subband than the blue subband, right? And the mobile that's talking to this, the 2 mobiles talking to this base station, this mobile is closer to the edge of this sector, and is actually able to really see the difference between the 2 subbands. It informs this base that I'm seeing more interference. So that's sort of what I've done here to show that is make the line thicker. So this mobile is feeding back information about the quality of the interference that it's receiving on either of these subbands. And the same is being done by all the mobiles in the sector, right? So this base is able to decide which band to allocate this mobile to versus that mobile, right? Because it knows how much interference is being experienced in either case. So we have the information to be able to avoid interference. At least if this pattern stayed the same, then you can do the allocation here. But what's complicated here is the fact that all of these base stations are doing it all simultaneously, and will it ever converge, or what is the optimal objective and allocation scheme here? I mean, I'm just giving you a hand-waving explanation of why it may work, but right, will it really work, and what should be the real objective?
Each mobile is going to be given only one subband.
Right, for the sorry.
While clearing for both blue and pink.
No, that is the channel quality information that it's feeding back, right? This is actually talking to this base. I mean, it's receiving from this base, right? This is interference that's seen by this mobile, right? To make a resource allocation here, this base is using the CQI information fed back for each of the subbands.
So it has to send the CQI information for all subbands?
That's right. That's right. If you have to do the scheme, you need to know that. But as I said before, you only need to send that intermittently, not in every slot, for example. Because if you're really only tracking the interference on an average time scale, then you only need feedback, say, once every 50 slots or 100 slots.
Well, one user lives in one subband or in multiple subbands.
In one subband.
So maybe that's what this question is. If one lives in one subband, how does it send information for 2 subbands?
Oh, when you say live, what we mean is it provides, I mean, you allocate resources in that subband for transmission of information to the mobile. But the mobile is, of course, the radio and the mobile is listening to the whole band. Okay.
Figure out in which subband to transmit it first, sees interference in all subbands. That's what I'm telling you.
That's right. That's right.
Yes.
Right.
Okay, so that sounds like an extra kind of feature.
No, well, if you think about it, the OFDM systems are designed so that you do a single FFT that spans the whole band. right?
Right.
And you have to listen to the control channels, and then that's how you know. So it's not like the receiver is just designed to work only on a single subband. The receiver is doing signal processing for the whole band anyway. It's just that its resources are coming in some subcarriers.
No, I know that, but
Right. Yeah, you need additional feedback on a subband level, right? Yeah, that's how we avoid the exchange of information over the backbone, right? It's sort of sent back through the mobiles.
This reporting is for the base that you're talking to.
That's right. You only report back to the base that you're talking to.
It's becoming classical in terms of probe. If you don't have probe over here, you will kill the receiver.
Yes. So, for example, this doesn't have may not provide any information about this separation, right? So, if all of your mobiles are close to the base, yeah. So this base has no preference to do any allocation, but that's okay because it's going to be sending lower powers for the same traffic load. All right. So I'm going to now describe the actual algorithm in the next two charts. So the algorithm is or the objective of the algorithm is to minimize the power transmitted in each sector selfishly, right? Based on the feedback that's provided. So just some notation before I can formulate the optimization problem. I is the flow index, J is the subband index, and Mij is the quantity that refers to the number of sub carriers that are required to achieve the target number of bits to be sent in each slot. Okay, so we know that voice over IP one packet is 128 bits. So suppose I want to send 128 bits in this frame. How many subcarriers do I need? That's what this Mij is. And Pij is the corresponding transmit power, right, required to achieve that many number of bits. And Aj and Bi are the set of or sets, and Aj is the set of users assigned to the resource set J, and Bi is the resource set assigned to user I. So they are inverse mappings of each other. Okay, and this is where the CQI gets used. We talk a lot about the channel quality information. That actually goes into the computation of this Mij and Pij.
So set is one subcarrier and a time slot.
Well, I'm sorry, resource set is like a subband. Okay, it's a subband. Well, the reason it's more general than a subband is because you can think of it as a combination of slot and subband, but you can just think of subbands for now. I mean,
It doesn't include power.
yeah, power is a user level quantity, Pij. Okay, the subband power is going to become the aggregate of all the powers that are assigned for the different users.
so the user can have more than one band.
Well, these are quantities that are used in the algorithm, but you'll see that the allocation forces the user to be on a single subband. But these quantities are computed for all the subbands.
So Bi is going to be size of one.
Right, exactly. That's right. That'll be 1. Okay. So what we do in each sector is basically this. Okay. You minimize the total power that's assigned to all of the users. So sum over the Pijs in all of the, I mean the I belonging to the band J, right? Or all the users belonging to that subband J, and then sum over the subband. So essentially this is the total power that the sector has to transmit to meet the target rates. Okay. Our goal is to minimize that, and of course we have the constraint on the number of subcarriers in each of the subbands. We can use more subcarriers than that are available in a given subband. So it's as simple as that. So this is the optimization problem that's being run in each sector to make an allocation, right? Oh, the number of subcarriers in a given subband. Okay. So that's this constraint. So the first question is it really going to work? I mean, you can do this using the feedback which is captured in Mij and Pij. It turns out that it actually does the job if you do this, but in a slow fashion. That's critical. So first of all, a direct solution of this is fairly complex, right? We know how to compute the Pijs, But solving this is like solving an integer linear program every slot for all the users. It's very hard to do. And even if you are able to do that, you could end up with solutions that are very different the next time you do this. So that means like moving users, the resource allocated to the users has to be shifted around at the next instant, next time you run this algorithm. So those are some of the main issues that we have with this. And even if you were able to do this, right, do the signaling, if you were to take this approach, you would run into trouble because you're not able to adapt slowly to the changes made in other sectors, right? So you never really get a good feeling for the subband power levels from the neighboring sector. So inherently your scheme has to be something that makes changes slowly, and that's the crucial observation here, and that's what we do. So our algorithm actually solves this problem, but over time, not instantaneously. Yeah.
How is the interface modular? You're just saying that for each subtype J, you're seeing all users who are in that subtype, but in some subcarrier of that subtype.
No,
Powers and
right. So the interference is captured in the calculation of PIJ, right? So the user is feeding back some channel quality.
for the PIJ, that PIJ will achieve some.
Right.
Oh, okay.
If there's more interference, the PIJ will be larger.
Last thing is just, then that's, and even there are transmit power constraint on PIJ for each user J.
Yeah, well, we have an aggregate transmit power constraint. Of course, you can only accommodate as many users as this sum is less than the total available power in the base station.
This is downlink, remember?
Downlink, yeah.
This is the power. If the minimum power is large, you can have
So it's a counter.
Right, yeah. We have a sum power constraint across all the users.
There's one thing that you do prescribe is this MJ size, right?
Yeah, that is our algorithm works for any NJ. I mean,
Of course.
so but we take what's in the standard. So standards have defined 4 subbands. So if it's 5 megahertz, you get about 128 carriers on each of them.
You could conceive a problem where that is also.
Yeah, of course you can. Yeah, if you really think about it, if you had a large number of subbands, then it's like optimizing the NJs, because 2 of them might have the same power profile.
Right.
Then it's like having a larger one. Okay, up to some level, it's the same problem. Yeah.
So do you consider the interference to the neighboring sectors in the same cell?
Right. The interference is that's also included in the CQI that's sent back, right? So okay, I think what you're asking is, from a base station, does it explicitly consider the power transmitted on the neighboring sectors? No, it doesn't explicitly take that into account. It only is captured in the PIJ just like any other cell. So there's no local coordination between the sectors in this algorithm. Although you could probably conceive of using that because it's easy to do. We are not doing that here.
But consider the cycle of the antenna pattern.
No, there is interference. Yeah, of course. Okay, so the model does take into account that there is interference from the neighboring sectors. But what I'm trying to say is there is no explicit information exchange between sectors of the same cell even. Okay. Yeah, but that interference is modeled. I mean, it's like any other cell, whether it's a sector or another cell, it's treated the same way. All right. Okay. So how do we do this thing slowly, right? And this is where work by Sasha that he done before comes into picture. So in his previous work, he had studied a completely different system where you can solve this any general linear program over time by thinking of it as a queuing network. Okay, so in this particular case, we can think of these different users that for whom we are making allocations as traffic sources that have to be routed to a certain set of servers that have certain capacities, right? And the costs, there's routing costs associated with it is sort of like the PIJs. So basically, the mapping to the queuing problem happens by setting up these token queues for powers and subcarriers. which you can think of them as just counters, right? So you count the amount of power being used for each of the users over time, right? And you drain the queues at a certain rate prescribed by the constraint. And as long as roughly these are stable, these queues remain stable, that means you're meeting the constraints. Okay? And this is so a particular example of the utility maximization algorithm subject to constraints. So to be more specific, what the algorithm does is the following. So for each flow, we compute this objective function. Okay, we know the PIJs, and the QJs are nothing but the token counters for the number of subcarriers used. Okay, so you can imagine how this thing works, right? If the queues are large, that means you're putting too many users in a given subband, then this algorithm will discourage from putting more users into the same subband. And this term here captures the fact that you're using more power in some subbands and less power in other subbands. So this makes sure that you tend to put the users in those subbands that for which it requires less power, as long as you're not putting too many users in that, right? That's the basic idea. It's very simple. I mean, if you want to minimize the power, you put the user in that subband that requires the least amount of transmit power. Except that you have to make sure that you don't put too many of them, so that it starts to violate the constraint, right? So that's what this achieves. So for every flow we calculate this and then update this quantity because the user is going to be put on a particular subband, okay? And remember these were like token counters of queues, and which can be drained at a certain rate because you have that many subcarriers. So for each subband, you do this whenever you run this algorithm. So in this case, in this example, I'm thinking of it as being run every slot. So in every slot, we can remove these many subcarriers from the total number of subcarriers used. Okay. And finally, although this is computed every slot, you only update the user in the real allocation. So that's why, by the way, it's called shadow algorithm. I forgot to mention that. It's a shadow algorithm because it's running, it's really running a scheduling algorithm or an allocation algorithm, but that is not providing the instantaneous decision. So you run the algorithm and determine where the users should be assigned, and then a real allocation happens, taking into account the integer constraints and things like that. Here, for example, the MIJ could be a fraction because it's the number of subcarriers. You can treat it as an arbitrary number of subcarriers. But the real allocation is rigid. So going back to step 3, we would move the user from one subband to another subband only if the objective function is improved significantly, right? To the extent that you get a reasonable improvement.
So that do you take the consideration that every user should get the same rate? It's a constant rate.
Right. That's the computation of PIJ and MIJ are rate dependent, right? How do we get PIJ? It's the amount of power required and number of subcarriers required. They both depend on the rate. All right. So there are other practical aspects that need to be taken into account, like the power control and hybrid ARQ and all that. And that's easy enough to do. So this has an effect on the shadow algorithm only through the PIJs and the MIJs. So as we run this power control algorithm, which basically updates the transmit power every time you fail to meet the target number of transmissions, right? So the way these systems work is you decide that you want to complete this packet after 4 transmissions, right? And you have an algorithm running. I mean, the receiver is feeding back X and X, which tells you whether you transmitted in 4 transmissions or 3 transmissions or 5 transmissions. So if you whenever you take 5 transmissions, you increase the power because you took too many, right? That's how the power control works. And when we run that power control algorithm, the effect of that is captured in the PIJs. Okay, this is supposed to be a J here, right? And we right now change all of the PIJs even though the resources is assigned only on one subband. Okay, these are some of the details to connect the basic algorithm to the real system. All right, in the interest of time, I'll probably skip this. I think all I'm going to say is that this, in terms of the properties of the system, we can show that in the two-user, two-cell symmetric system. So if you take the case where you have just two cells, okay, in just straight line, just two cells, and a bunch of users that are at the center of the near the center and near the edge, and symmetrically in the next cell, right? Like the picture here, right? If you had just users here and symmetrically here and here, then we can actually analyze the algorithm in this case, or a version of the algorithm, not exactly the same one, but something that's closely approximates the algorithm, and then show that nice things happen, right? I'm just going to leave it at that. So, which means that you actually have convergence by, even though each of the base stations is adjusting the transmit powers independently, eventually the system converges to a Nash equilibrium. Okay, and the convergence point is the minimum power allocation point in this particular case. Okay.
So could you try to get the loss efficiency when you have this sort of independent operations of base stations compared to what it would have been the work one?
Yeah, so in the two-user case, I think it's optimum, right? Even if you had coordination. But in more general scenarios, no, we don't know, because we don't know what the optimal is. It's very hard to say. For given instantiation of the user locations and traffic requirements, you have only way is to do a brute force search and try to find out what's the best. And it's very hard to do that. Even for 3 cells, I think it's too complicated.
So even for two-user case, how fast is the convergence?
Oh, it's very fast in terms of you could I would say 4 or 5 steps. If you write down the iterations manually, you can even analytically see that it happens in a very small number of steps. But when I say steps, it's user moving. But the power control iterations also are happening within this. Remember, when a particular cell adjusts the power, the other cell has to respond to the power adjustments, right? So there's power iterations within each user movement. So I'm just thinking about steps as the number of times the users have to be moved around, and that's a very small number. Now the other thing we can state about this algorithm is, in the general case, is the existence of a Nash equilibrium. So if you think of this as a game that the base stations are involved in, with the payoff for each base station being the amount of users that it's allocating, right? Actually the power used by the users, not the number. Well, it's related to the number of users, but more specifically the power that required to satisfy the constraints of transmitting a certain number of bits. So if you think of that as the payoff and the strategies as basically the way you allocate resources to users, then you can show that there's a Nash equilibrium. It converges to that. I mean, not convergence, but there exists a Nash equilibrium.
So the general case, not just 2 years.
Yeah, this is the general case, but we're not saying any convergence in the general case. Okay.
So you showed us a picture of the converged bars, right?
Right. This is just a two-cell case.
Yeah. Okay. So in the 2-cell case, you always get this.
Right. Either you get this or the flipped version, of course, the isomorphic version. Right.
But in general, you get some.
Yeah, general. I'm going to show you 3-cell case, for example. So we just for study here, we just consider a simple 3-cell model with users distributed in this cell, in the center of this cell, in a variety of ways, and the parameters are typical. We just so the first result I want to show is how the algorithm actually produces the pattern. So on this side we have 3 charts, right? One for each of the sectors. Sector 1, sector 2, sector 3, and this is the normalized average transmit power on each of the subbands. Again, 3 subbands. Okay. So what you see here is they form a nice pattern in terms of each of the sectors transmitting on different subbands, but then still using some of these. So that's more clear here. If you look at the number of subcarriers assigned, it's true that they separate into using these 3 bands for the most part, but a substantial number of subcarriers are used in the other sectors too, but with very low power. So this is critical for efficiency. So we are not talking about hard frequency reuse, right? So efficient fractional frequency reuse is through power adjustment. Okay, that's something that you see from this. But the more interesting thing is that you generate patterns automatically. Yeah, it probably converges to a Nash equilibrium, but we can't say that it converges to that. I mean, to a Nash equilibrium. I mean, locally, I guess it is. I guess it's locally has some domain of attraction around this point. So maybe it is.
So what's the? Can you show the picture of these 3? The 2-dimensional picture. What's the location position?
Okay, I don't have a picture for that. We didn't capture that, where the user is, but you can imagine what happens is, okay, so users that are really close to the base, they don't care which, they don't have to be in this one, right? They don't experience that much interference. So they generally tend to fall in these. Some of them will be here, but they're agnostic to which subband it is. But users that are close to, that are here somewhere in this neighborhood, they don't care about this base station. So this set of users and users here will share the same band. Okay, so that's how it works. So it's really like a 2/3 reuse roughly, because very few users really see interference from both the sectors. Okay.
So there's a lot of symmetry, so assume that the 1 and 3 are blue and red, and then the middle one is the...
Right.
Based on the diagrams.
Mm-hmm. Yeah, I mean, I don't have a picture showing exactly, which user goes to which band.
But what I'm saying, like, you have symmetry between picture 1 and 3.
I'm sorry, here? Yeah, it is symmetric, right.
The middle one is different, and that probably is related to the...
You're saying this is different from this?
The middle one seems to be
somewhat different?
Yeah.
Yeah, the one reason could be that, we are just running this for a particular instantiation of the users, right? Of course, it's a large number of users. In this case, I think it was 120 or 45 or something like that. So maybe that doesn't fully explain this. Well, I mean, there is some differences, I agree, yeah. But I guess the main point here is the pattern that comes about.
Right. Okay. Yeah. I'm saying that because, like, if you look at the height of those big ones in the number of carriers,
right? The
one in the corner looks the biggest, and the one
right.
The little one looks
it's a little smaller. Right. Okay. Yeah. All right. So in terms of capacity improvement, it provides about 20% improvement, and these two pictures show how I compute the capacities. So this one is the normalized total sector power. So we just did a minimization of the power, but you have to check that the power is below the available power, right? So this chart shows you the complementary, cumulative distribution function of the power used. So we can tell that, if 1% of the time, you better be, you allow for larger than 1, less than 1% of the time, right? This is the normalized sector power. So you don't want to exceed 1 more than 1% of the time. Okay, so that's the criterion we used to say that certain number of users is supportable or not supportable. Okay, and similarly the delay, the normalized average queue size, which is what we captured, is a measure of the delay that's that these packets are encountering, and we don't want the delay to be more than, in this case, just 1. I just said 1 packet delay at most because it's an average delay.
Just average.
That's right. The worst case delay, yeah. That would require more detailed simulations to keep track of, delay per packet and capture all that. Okay, but this gives you, I mean, by making this constant really strict, it shows that the tail cannot be, I mean, even if the tail is 3 times, right, you're still okay because it's only a 60 millisecond delay in terms of voice or IP packet delay.
Because Q will be like exponential, so the tail will be much more than 3 times, right? From the mean.
Well, I mean, the probability that it exceeds 3 times this would be pretty small. I mean, I'm saying that the mean, okay, the mean has to be, mean is less than 1 or greater than 1 at most 1% of the time. So then if you look at 3 times the mean and ask how often it's going to exceed that, I don't know, I mean, something like that. It has to be quite small. But anyway, the point is we are using the same metric for both the baseline and our scheme. And there's no reason to expect our scheme to have a worse tail than the baseline, I think.
How do you compare the gains? You're saying 20%?
Right. So in terms of number of users that can be supported in this particular setting, right? And it depends, remember, on the cell edge SNR, which is 10 dB in this case. Now, why is that? Because the amount of interference experience is a function of that, right? The higher the cell edge SNR, the more interference there is, and so the better the scheme will do. In fact, if I change it to 20%, 20 dB, then the gain improves to 30%, just because there's more interference for avoiding. Okay.
So even if you increase the number of subband, you will see more gain.
Well, in the 3-sector case, we don't expect much improvement in the gain with more. In fact, I have some pictures with more subbands. Okay, later on, we see that the capacity doesn't increase that much beyond this. I mean, yeah, yes, that's true in a big 57-sector simulation or in a real system, but in this case, you don't expect that much of an improvement because there's only 2 interferers, right? So how much resolution do you need to do this kind of stuff? Okay, so this picture shows how often we change bands. Okay, so number of band changes is in terms of number of users that are moved around, and it's really a small fraction of the total number of users being scheduled, right? Because it's across all 3 sectors, and this is time slot. So you can see the worst case is like 11 out of 300 plus users that are in the system. And I will not dwell on that. Sorry.
Have you somewhere along the line said, like, there's some other resource scheduler and we're using this just to update the powers of the ones that recently dictated by that? Or this algorithm for that to be shadow?
I'm sorry.
Like, have you said, I mean, there's some scheduler.
Right.
We're using this as a shadow algorithm to update the powers for the band allocations of that default algorithm.
That's what you're saying is really true for the best effort case. We build off of, say, proportional fat scheduler or something like that. Here, the baseline scheduler itself is just only decision it's making is which band to assign the user to, which subband to assign the user to.
So once they're assigned, you're just changing the powers. So you're trying to.
Oh no! The shadow algorithm is actually coming up with also which the decision as to which subband the user should be assigned to. Okay, and the power, of course, is once you decide the subband, the power calculation is default in the sense that you have to meet a target rate, so you have to make sure that the power is sufficient to do that, right? So the real purpose of the shadow algorithm is to decide which subband to assign the user. Okay, so here is the case where we did some non-uniform distribution of users. So this is, I think, the case where, sector 1 has all the users close to the base station, okay, and sector 2 and 3 near the edges. So you can see that the sector 1 is pretty much uniformly using all the subcarriers and transmitting on all of the subcarriers. Of course, there is still some sensitivity here because when I say center, it's not like zero interference from the neighboring cells. It still sees some interference. On the other hand, these two now clearly avoid each other. Okay, and use some of the bands, rest of the subbands as well. Okay, and if you compare this case to the baseline, we get a larger improvement, just because the sector 1 is not transmitting as much power, so it's a 2-sector scenario, so the improvement is larger. And we played with 4 bands and 6 bands, and we still get the algorithm to work properly, and we get this almost the same capacity number. In fact, it's slightly smaller than the 3-band case, and we think it's because of the inefficiencies, the statistical multiplexing inefficiencies. The more bands you have with the same number of subcarriers, what you lose in each subband increases, right? So you need like 3 or 4 subcarriers per user, but now if each of them has has only 10 or 12, then you lose out on a few. So that's coming into play as well.
So here, do you see any rate loss in convergence? Convergence rate?
Oh, because it's more number of bands. Probably yes, it takes more time to converge. Yes, that's true.
But beta in the algorithm is your convergence kind of control.
There's one parameter here, the beta, which sort of weighs the two, and there's a delta which actually also controls convergence in the sense that it decides how quickly you can move users from subband to subband. So the faster, if the more quickly you allow movement, or it's hard to say that it increases the convergence rate though, because
It's very hard for you to gauge that because there's no dynamics. You have just a bunch of users. You don't have a mission control.
no, yeah, well, the thing is, we start the system off with there's dynamics through the activity.
Yeah, but
It's not controlled.
over a long time. You have the same number of users. And
Right.
all of them have the same CBR.
I wouldn't say over a long time. Yeah, relatively. Yeah, I guess it. Yeah, there's enough time for it to converge before activity changes. Right.
So you don't have users coming in and going out.
We do. Through the activity, right? I mean, your talk time is modeled as exponential with some distribution, right? Or on time and off time. So the user leaves the system as soon as his talk time is completed.
But the average number of users is fixed.
That's right.
Across sectors, there is some uniform power average transfer. Is that what you're saying? It will go 4 to 6.
4 to 6, yeah. It's my only observation here is that there is still clearly a pattern that's there that avoids interference, but there's too many. Yeah, so like for example, these two are sort of identical here, but not necessarily there. But the thing is, when you have excess number of subbands, then you need for interference avoidance, you are likely to see equal powers in some of them, right? There's really no need to have that many subbands.
So the message is we should not have that many.
It's better not to have too many, right?
It's killing the algorithm.
It's as I said, it's not killing the algorithm in the sense that it still produces almost the same capacity, but it's definitely less by a very small percentage because of these statistical multiplexing.
Two bands which are on the same path, they could have been clubbed in.
Right, they could have been clubbed together in one. Right.
You don't need to.
That's right. Okay. All right. So I have maybe a few minutes to talk about this, if it's okay. Okay. Things are okay. Let's start out by saying what you could do in the best effort traffic. So first of all, best effort traffic is like web browsing. It's long packets that are waiting to be sent, right? And or like a file transfer is probably better for our example here, which assumes essentially every user has infinite backlog in the buffers, right? It was a standard assumption for the proportional fair scheduling, etc., to study the performance. So anyway, the delay is not a big issue here, and you are trying to maximize the overall sector throughput subject to some fairness criterion. And the standard criterion is the proportional fair criterion, which is mapped into saying that you want to maximize the sum of the log of the throughputs, right? This has been shown to be providing proportional fairness. So just like we did in the CBR case, you could say that we want to do proportional. We just individually each sector would maximize this objective, right? Do the resource allocation to maximize this objective, and hope that some pattern emerges, which is kind of what we did in the CBR case, right? We minimize the power in each sector, and somehow we got those patterns. So if you start out by trying to do that, and this is just an online version of achieving this, right? If you use the scheduler weights as 1 over the average throughput, and the rates that are now band specific, and then you again a function of the channel quality and the number of subcarriers that are assigned, right? So you want to be constrained by the total power used and the total number of subcarriers in each of the bands, right? So this is basically the optimization that would maximize this in the long run. If you did this, to our surprise, even, I mean, I wouldn't say to our surprise, but we hoped something will happen, but nothing happened. And the reason we believe is because the interference is changing fast in this case, as opposed to our CBR case. Remember the point I made, that the main reason I think it worked is because changes are happening quite slowly, and the interference powers were stable. So as each sector adapts, other sector doesn't react instantaneously and mess up the mess up the pattern essentially, right? So there's the patterns actually emerge, but here it didn't work that way. So if you had to selfishly do this throughput maximization in each sector, we don't see any patterns emerging. So you have to force the patterns to emerge by using some additional weights, which force the individual base stations to put users or scheduled resources differently in different subbands. So here we have two versions of this. In this case, we have the weights B sub j in each sector, one for each subband, right? And you set it up so that the BJs are different in the different sectors. So you would have, say, 0.5 and 0.5 and 0. So that means you're kind of, or the other way. So a large number, let's say 0.5, 0.5, and 10. That means you're making it really hard for the first sector to use the third subband. And in the other sector, you do it the other way. So 0.5, 10, and 0.5. So that means, yeah, so that's the problem. So that's one of the drawbacks of this algorithm, is you have to do the equivalent of frequency planning, right? Essentially, you have to decide what the weights will have to be to create this pattern. But the pattern does emerge in this case because we are forcing it in some sense by making the scheduler prefer certain bands over other bands, right? But you do need to plan to come up with the weights. And the other problem is the FFR pattern that comes out is not automatic. It's in some sense induced by the weights. So what you get is sort of what you put into the system.
Okay, so let me understand. The
Right.
previous slide says what you're saying you can't converge. Is that what you're saying?
Yeah, here, yeah, we just think that that's the reason. There's no, you always end up with the equal powers on all the subbands if you did this. That's what happens.
When you say interference changes too fast, it is because of the traffic pattern?
Right, so the base stations are still assigning different powers to different subbands, depending on who they schedule on each of the subbands, right? Now this is happening in all the sectors, right? But the users that are scheduled from slot to slot are different. So the first slot you might be scheduling, maybe all the good users on all 3 subbands, right? And that causes a certain power profile. And in the next slot, you're changing to a completely different set of users, right? That gives a completely different power profile. And this changes slot to slot. So, and the feedback is averaging out these things. Remember, the feedback is once every 50 slots or so. It's only providing an average interference level.
So you're assuming that users get small packets and not a long file so that
Yeah, I mean, I think that when you try to do this optimization, eventually it does switch, right? From like there are multiple users of each kind. So I didn't, you're right. To maybe Sometimes it lasts for a few slots, but it's not long enough for us to see any clear patterns. That's all I'm saying.
Is it because in the previous CVR case, once a user was scheduled, it's just a constant running state there till this.
Right, exactly.
The interface pattern was kind of static.
That's right.
Over here, since each user should transmit some long file, but in each slot you are dynamically.
That's right. That's right.
Maximize the object.
That's right. That's my intuition, right? Yeah.
It's like the model where it's like CVR for a short period of time, and he comes back and joins the queue. That kind of model. This is the best effort kind of model.
Yeah, well, you can see, we don't know, I mean, yeah, user may be scheduled for multiple slots together, that's allowed, but even if that's the case, it doesn't happen for very long because we have these fairness metrics that forces you to schedule other users.
So, but were you able to solve that problem?
In the
Previous page?
no, this is one solution. I'm going to show this.
You said
Right, that one, we solved that by imposing these additional, see, this one is identical to the previous one except for these terms, right? If you think about it, the online algorithm is the same as before, but we added these additional terms.
right, but you said you saw that the power allocation was constant. You didn't get any FFR.
That's right, not in the previous optimization. But in this optimization, it turns out that it actually works.
You get that our patterns based on VJ.
Exactly. Which is not you would expect that.
So the implication is there is protocol level source agreements with users. Is that what it is? Like,
Yeah, protocol will, there's signaling from the base station to tell the users which resources are allocated. Right. Of course, all of this assumes that there's a signaling protocol that does the scheduling every frame. Okay. So as he said, this means that you need the BDA. So we decided that wasn't good enough for us. So we still wanted a no planning approach, right? So we said, okay, let's do the scheduling algorithm as you normally do, proportional fair, but now let's make sure that the power levels are not changing very rapidly. Okay, so we use a shadow algorithm sort of thing to come up with power levels for each of the subbands, and then the real algorithm uses this set of powers in its scheduler optimization. Okay, it's like running the first algorithm but with separate power constraints for each of the subbands. Okay, and the power constraints are derived by the shadow algorithm. Okay, right, and we tune the shadow algorithm so that the powers separate from in the different sectors. Right, so through the power levels that are computed here, there will be a pattern that comes from running the shadow algorithm.
Isn't it a tougher problem to have power constraint for each subline?
Tougher in what sense?
In the interest of optimization, when you have like per band power constraint.
Well, we are still using simple greedy algorithm there. Of course, we are not saying that we are optimally solving the OFDM resource allocation problem, right? That of course is a hard problem if you take the frequency selective fading and all that. It's just a simple greedy algorithm that was used there. Okay. All right. So how the shadow algorithm works is again based on the CQI feedback, right? That's the information that's there to decide which bands are better for users in a given sector, etc. And the way it works is, it's a little bit sort of ad hoc, but this is what Shasha came up with. We determine in the shadow algorithm now which user. So we run this multiple times within each slot or every so many slots. Okay, when we want to set up the power level. So you first randomly permute the bands. It turns out that that's important for this algorithm. Otherwise, you get locked into some states that are not good enough. So we change the order each time we cycle through the bands, and then for each of the bands we figure out who's the best user according to the standard scheduling criterion. Okay, and then decide whether to add more power to that subband or not. So this is a new piece, right? And you would add more power to that subband if it satisfies this criterion. Okay, and every time you add the same amount of power, we have this constant P star which is what gets added to the power in a moving average fashion or exponential averaging fashion, right? So this means that the powers are not changing very fast. So we make a decision based on the utility that the user achieves relative to the current power that's been assigned, right? If the utility is high, then you add more power to that subband in discrete quantum steps like P star, weighted by this exponential smoothing constant.
Like genetic algorithms have some notion of elevating the temperature slowly.
No, I think this is not related to that. Here we are just, it's similar to the CBR in some sense. So as long as, you can think of putting power tokens in bins, and then if you're not using excess power, then you just greedily put more power into the band that gave good utility. I mean, if the band gives sufficient utility, then you put more power into that. And it turns out that this sort of works and creates bands without any artificial BJs, etc. Okay, but the key is to make the powers change slowly so that you can achieve some convergence.
There's a notion of P star, which is the amount that you decide up on.
Yeah, that you have to decide in advance, but that's not being changed anytime during the algorithm. That's fixed. So essentially, the intuition is by making P star bigger than P tot by J, you're putting more power into subbands, which is what is causing the separation of powers, right? So if you put more power than the average into a given subband, right, and still maintain the total power constraint, then clearly you can't put as much power in all of the subbands, right? So you look at the utility achieved and then put more power into a given subband. And that way you create the patterns, and it turns out that it does work, and okay, it does create patterns. And then I didn't bring with me all the patterns that it creates, but at least we compared it to the baseline. So the universal is the red line, which is the overall, it's just the standard proportional fair without any FFR. And the blue is what we get with the shadow algorithm, the one that I just described, and this is with the BJ weights that are applied, okay, with the hand cranked BJs, of course. We didn't spend too much time optimizing the BJs, but you can see, and this is full 57 sector 20 user type simulation. And you can see that if there's some improvement from this, especially if you run the proportional fair as it is and look at what the cell edge throughput is, then this kind of creating these patterns significantly improves the cell edge user throughput. But of course, if this was your goal, maybe proportional fair wasn't the best algorithm. But I'm just pointing out that if you did this and then looked at it this way, you get a big improvement, and overall sector throughput improvement is also there. This curve is always to the right of the proportional fair curve. Okay. So we actually looked at it as did a simulation with the minimum rate so that we can actually make this as the criterion. On the x-axis we plot the 5 percentile throughput, okay, and the y-axis plots the metric, because we are doing proportional fairness. The right metric here is the log or sum of the log of the throughputs. So we plot that versus the 5 percentile throughput. And these different points are running the algorithm with different values of minimum rate, right? If you set the minimum rate higher, then you can get a larger throughput, 5 percentile throughput, cell edge throughput. Basically, you're forcing fairness in a particular way, okay? So we get this curve for the universal reuse, and these two curves is what we get for the two different algorithms. And you can see that this is falls off pretty sharply around this point. That means this, even by tweaking the Rmin, you cannot achieve cell edge throughput larger than this, or at least a 5 percentile throughput larger than this number, around 4.5. Whereas you can get 33% improvement with our shadow algorithm. Okay, so you do get a substantial improvement in the cell edge throughput, even when you design the scheduler to to maximize the cell edge throughput, subject to the fairness or sector throughput criterion. And if you want to look at it this way, you get, I guess, the entire sum log throughput improvement at any point is about 20%. You know, if we compare this to that, or maybe this to this, something like that. All right, I think I'll just end with that. I ran over a little bit. So I think we have developed some good distributed coordination strategies that are very simple in the sense that they are run on each sector without any coordination between base stations. And you can combine the algorithms with other schedulers that people are using, or you know, to meet the required traffic and QoS demands. Now, we haven't explored this that much, but maybe you know, if you're not interested in any sector throughput metric, then you can get even larger gains in terms of sector cell edge throughput.
So if you have a sum log curves, right?
Right.
Is it like dB? Should we really say something like 6 dB gain?
Yeah, it is a dB gain which I translated into a percentage. It was, you know, 43 minus 40 is the sum difference in the sum log for 20 users, right? So you can translate that into a percentage by saying it's the equivalent of, you know, e power 3 over 20.
So is it 3 dB? Is that 100%?
Yeah, 3 dB would be 100%, but this is not. It's first of all not in dBs because it's not 10 log. It's log to the base e.
Okay.
That's the difference. So that's why I'm raising it to the power e. All right. So that concludes my presentation. Thanks for listening.